My name's Clive Johnson. I work for Foundry 42 UK, where I'm the lead network programmer working on Star Citizen. Today we're going to talk a little bit about serialized variables. So what are serialized variables? Well, they're not really something that you can see in the game, and ideally, if everything's working the way it should, then they're not something that you really ever need to think about. But they are the answer to a question, which I think is quite important, and that's how do you network a game like Star Citizen? One of the first times I asked myself that question was shortly after I joined the company. I think my first reaction was one of sheer terror. Tears, panic, and once it kind of calmed down and the tears had stopped, you do what any engineer is going to do when faced with an impossible problem. You try and break it down into smaller, impossible problems. When trying to answer the question, how we network Star Citizen, one of the first things we've got to think about is exactly who's going to do the work, who's going to network everything we have in the game. Now, Star Citizen itself is made up of thousands of different elements, and some of these are visible, like planets and ships and players and coffee cups, and others you don't see, like missions or the logic assigning out landing pads. Each of these elements is really a different type of entity, and each type might be used thousands of times throughout the game. But all the types behave in specific ways or have certain uses, and that has to be implemented in the code. And most of them need to work in both single player for Squadron 42 and multiplayer for Star Citizen. In other words, most of them have to be networked. So who's going to do the work? Well, currently we've got about 60 engineers coding different parts of the game, but we have only 6 network programmers. Half of these work in Austin on back-end services, and that includes our core online services such as matchmaking and friends and player authentication. The other half is my team here in the UK, and we focus mainly on the networking between the client and the server. So it's kind of up to us to make sure that all the entity types are correctly networked and everything's functioning the way we'd like it to in the multiplayer game. But with 60 programmers or thereabouts writing new code and making new entity types, if we've only got 3 actually making it work in multiplayer, my team needs to work about 20 times faster than anybody else. We're good, but we're not that good, so clearly leaving all the networking to the network programmers is not going to work. So what we need to do is have every engineer make sure that their own code works in multiplayer. But the problem with that is that network programming is really very hard, and it can take years to learn all the different ins and outs. So we need a way to simplify it so that non-specialists can learn everything they need to do in just like a couple of hours. What we need is an API, which stands for an application programmer interface, and that's really a cushion between a programmer doing the work and the problem that they want to solve. The API kind of simplifies things by allowing the programmer to say exactly what it is that they want to do, but without saying how it should be done. So you can kind of think of it like driving a car. So obviously you've got your steering wheel and the pedals and other controls, gear stick, whatever. That's not how the car drives. They're just the controls that tell the car what to do. So under the hood, the driver's commands are turned into different settings for like fuel air mixture or engine timing or hydraulic pressures for brakes and power steering. And that's kind of the interface part of an application programmer interface. By building the right set of controls, you can change how the API actually works without having to change the code. So what about driver error? Cars equipped with assisted driving can take action when a driver makes a mistake and possibly prevent a crash. And we want the same sort of thing from the API that we're going to develop. When a program is using it, it actively prevents them from making mistakes that might cause us bugs or negatively impact performance. But we can go a bit further though. So currently the technology for driverless cars is being developed. When that happens, the skill needed to operate a driverless car drops to just saying where you want it to go. And this is what we've tried to do with our network API. Serialized variables are a really big part of that. By giving our programmers a simpler model to work with, they can quickly and safely network the game elements that they're working on. Meanwhile, as network programmers are freed up to try and ensure that the API not only works quickly and efficiently, but also it deals with all the problems that you can get while networking anything. So before we go any further, we probably need to talk about another question, and that's how do online multiplayer games actually work? If you were to see the game as programmers often look at it, you'd see that everything is essentially lots of tables of values. Every entity in the game has its own table, and each value corresponds to a different property of the entity. Because we need to know what each value's for, we've got to give them all names. So a table has 2 columns, names on the left-hand side and values on the right. A row in a table is what we call a variable, and that's mainly because its value can change over time. A ship might have variables for shield strength and how much fuel it's got left. Players can have variables to say whether they're running or walking. And most, but not all of these variables will have an entity called a position, and that's going to tell us exactly where they are in the game's universe. And even though we kind of need 3 values for coordinates in 3D space, we tend to think of position as a single variable because one part changes, the other parts tend to change. So when an entity moves, it does so because the position variable has been changed. That variable is not really just keeping track of where the entity is, it's actually saying where the entity is. Programmers can write code that looks at the values in a table that belongs to an entity, and we can use those values to calculate some changes to other variables, and some of those variables might be in the same table, or some might be in other tables belonging to different entities. So as the game progresses, these variables are modified according to the actions of players and AI, and these changes update the graphics that you see on screen, and they can trigger particle effects and sound effects. To make this work in multiplayer, we've got to take one machine, the server, and have that make the changes to the tables, and then the server then needs to copy the modified tables to all the other machines, all the clients, and it does this by sending messages over the network, a bit like a group text message. And if everything works correctly, the clients and the server all have the same data in the tables, and everyone's in sync. Now, entities in our game can have dozens or even hundreds of these variables or properties, and most of them need to be kept in sync over the network. There are a few ways we could do this, and probably the most straightforward way is every now and then just to send the state of all the tables. And that works really well for very small numbers of entities. But as the number of entities increases, then the bandwidth that you're using to do that increases, and if we're not careful, that can cause us other problems. We might notice that most entities in the game don't tend to do much until someone does something to them. So what we can try is not sending the table for an entity unless it has changed. But now the game code's got to keep track of which entities have changed and which haven't, and that can be tricky to get right. It's a manual process that the gameplay programs have to do. Getting it wrong means that in certain situations, the tables for particular entities will no longer be in sync. We call that a desync, and the effects of that can range from like minor bugs that are just little annoyances to completely breaking the game. And the only way to find these bugs is through lots and lots of time-consuming playtesting. Perhaps worse, we haven't really solved the bandwidth problem either. By adding more players, that means that more entities will be being interacted with and having things done to them. So more tables are going to be getting updated, and more messages need to be sent out over the network, and the bandwidth jumps up once again. We still need to reduce this. So we might notice that when an entity's table is modified, not all the values in it are changed. So instead of sending the whole table, we could try just sending a few of them at a time, so we can split the table into sections. And then we're saving bandwidth by only sending a section if one or more of the variables in it have changed. If we put variables that are likely to change together in the same section, then we can save even more. But now the game code's got to keep track of not just modifications to entities, but modifications to individual sections. And that's even harder to get right. We've also got to write some extra code to say which variables need to be put into which messages. And since different types of entities have different sets of variables, they also need different sections. So this extra work has to be duplicated for every different type of entity. So the thing that really kills this plan for Star Citizen is entity components. A component is really, it's just a piece of code and some variables that implement a very specific piece of functionality. So entities get built by plugging different components together, and by choosing different components that you want to plug together, that gives us different types of entities. If you need an entity that can move around and collide with other things, then you have to give it a physics component. Your entity needs shields, give it a shield component. The number of different entity types we can build this way grows exponentially with the number of different components that we have, but what also grows exponentially is the amount of networking work we've got to do to cover all these different entity types. So clearly this isn't really going to work for us. Our networking API needs to be smarter. What we wanted were controls that were as simple as those for a driverless car, and what we had felt like it was as complicated as piloting a space shuttle. So that's when we came up with serialized variables. So with these, gameplay programmers just need to write their code the way they normally would. They're adding variables to their components as they need them, and the only extra thing that they need to do is mark the variables that they want networked in a special way. And that just shows that these ones are ones that need to be serialized. Serialization is the process of packing up the data in a form that's more efficient and better suits being sent over the network or serialized to a file. This makes life so much easier for our programmers. You can see how the code on the left can be simplified and reduced to what's on the right. It's really just like writing normal code and calling out which of the variables we want serialized. The program only needs to write the additional lines that you can see highlighted in purple on the right and add them to their struct or class definition. And that tells the serialized variable system which members of the structure to watch and update. Previously, we would have needed specific functions in each class, one for net serialized for networking, full serialized for the save game. And if we wanted to talk to the persistent database, we would have needed an extra function, something like persistent serialized. In these functions, the game programmers would have had to manually look at the variables they wanted to serialize and write them out into the serialization stream. So there's lots of scope there for extra work and possible errors if they forget to add a variable. But now, when a programmer writes a new class, they can just mark up which of the variables they want to be serialized, and everything else is handled automatically and efficiently behind the scenes. And that all goes through one unified system that we can profile and optimize, as opposed to having to worry about optimizing literally thousands of different functions. Once the variables have been marked, there's no need to group things into sections anymore. There's no extra code to write. The API detects when something has modified the value of a variable, and it lets the netcode know so that that can deal with it. New API even writes the code to handle the serialization for them. And this kind of level of automation, it not only saves us time, but it eliminates human error, meaning we have a lot fewer bugs, and we can just get on more quickly and more efficiently. So because the netcode's now being told about changes to individual variables, we on the networking side have a much clearer view of what's actually happening in the game. So you can kind of think of it like switching to a 4K TV when all you've ever seen before was like grainy black and white. And we're kind of using this extra information at the moment so that we only send exactly what has changed. And that means that our bandwidth per update message, the size of our update messages, is now probably about as optimized as it's possible to get. We're also using this information so that we can profile what's being sent by the game code, when it's marking variables dirty, so we can see if anyone's hitting anything particularly quickly, and maybe there's a bug in the game code that needs looking at. Really, the only kind of other improvements that we're going to get from now on are by optimizing like streams of network messages, cutting out who's sending messages at all and how often messages are being sent. We can handle all that on the network side, on the netcode side. So it's kind of like I was saying before, where we've got this interface with the API that separates game code from what we need to do, and we can make our changes without affecting them. While we were working on this new technology, we noticed that one of the entity types started sending about 80% less data. And at first we just didn't believe that. We were certain that the numbers have got to be wrong, or that a bug's throwing away most of the data. It wasn't until we went back and we double checked everything that really we started to realize that this saving's actually real and that it's due to the new code. That's probably not going to be typical, but it still kind of shows that the difference this kind of approach can make. That's not entirely where the story ends though, because one of the other cool things about serialized variables is that they don't just work for multiplayer and networking. Instead of sending the different tables and values and variables between just server and clients, we can also store them in a database or save them to a file. And that means that for no extra effort at all, the gameplay programmers can use the same serialized variables for persistence, recording what the state of entities is in our persistent universe. And we can even use them for save games in Squadron 42. Personally, I think probably the best thing about serialized variables is that they're one of the cornerstones that we're using to build this big, seamless, persistent universe. Achieving that is going to require spreading the load over multiple servers. Because it's seamless, we're going to have these servers communicate with each other, and that's going to mean that there could be a lot of servers aware of any particular entity. So let's say, for example, an AI pirate. Now, we don't want all the servers trying to tell the pirate what he should be doing, because first, that would be just a complete waste of computing power. And the second reason is that the servers might not agree on what the AI should do next. So we need one server that's in charge of the AI pirate, and only that server can send updates for that AI pirate entity, and the other servers just listen to it. So the trick is going to be how we decide which server gets the final say. And we're going to do that with something that we're calling tokens. A token can only be held by one computer at a time. And when a computer's finished with a token, it just passes it on to the next one that wants it. So by linking serialized variables and tokens together, we'll be able to transfer authority from one server to another as quickly as flicking a switch. What that means for our AI pirate is that control over its AI mind can pass seamlessly from one server to another. And since different servers, at least initially, will control different regions of space, this combination of tokens and serialized variables will allow our AI pirate and everything else to move freely through this seamless, persistent universe that's being simulated by lots of servers all working together. So hopefully you'll agree that serialized variables are not only a key part of the current technology, but they're a building block for future ones. And that's really not bad for something that you're never going to see. But that's often the reality of game development, and what you see in games really just the tip of an iceberg that's being buoyed up by a mass of systems and technologies all working together, out of sight and fingers crossed out of mind.